Hello everyone, we'll be starting the discussion of compaction. This is second module of the syllabus, second part of the second module actually, compaction. Earlier to this there is a clay mineralogy. We'll be studying clay mineralogy a bit later. This particular part, compaction, will be including in first IA also because there are some numerical problems involved. It will be easier for you to solve the problems. That's why I'm taking this. Okay, we'll straight away go. What is compaction? And here I'm making use of e-notes of VTU given by S.K. Prasad, Professor of Civil Engineering, S.J. College of Mysore. Okay, it's his notes, most of it I am using for explanation. Now, definition. What is meant by compaction? It is simple. Compaction is the method of mechanically increasing the density of soil. Now, pictorially, if you want to understand, here there is a natural section of the soil. All this white air is put over here. All this blue water is put over here. All these solids are taken over here. So the volume remains the same. The weight remains the same. Only thing is here we have put it in three-phase manner. So total weight divided by total volume V1 gives you the density or unit weight, specific weight, we call it as unit weight. So bulk unit weight gamma B1. Now when you apply some energy, maybe by rolling, maybe by ramming, right, there are a number of ways how you can compact it. So when you ram it, obviously what happens is the volume decreases. So volume has become V2. So what has gone out of this particular space is only the air will be escaping. The water will be remaining the same. The solids will be the same, right? Sometimes water will be a bit more, but whatever it is, bulk density increases, right? But W2, I mean, the ratio of weight to volume, if you take W by V2, gamma B2, that is unit weight of the soil increases. But gamma B2, when we calculate total weight, right? Here also total weight, water is remaining the same. It would be wise if I can take gamma D into picture. So this one has to understand what we generally compare is gamma D. Now what is gamma D? If you remember the definition, it is weight of solids only or weight of dry soil on the numerator divided by the volume. Okay, sorry, so divided by the volume. Now in this case what happens is the number of solids or the particles weight is remaining the same here and here, but the volume taken, which was this much, now has decreased by some amount. If you can just observe here, so much of volume has decreased. So this volume is automatically decreased, but weight of solids is remaining the same in the numerator. Obviously the gamma D increases. So in compaction we make use of gamma D for comparison rather than gamma B. Here it is given as gamma B, but ultimately we compare gamma D. Okay, we'll continue with the next point over here. Compaction is the process of increasing the bulk density of soil by driving out air. Yeah, when you compact it, what you drive out is air, what escapes is air, the water is remaining the same. The densification of the soil is achieved by reducing air void space. During compaction, air content reduces, but not the water content. Sometimes the water content actually increases. We are going to see that in detail. Now from this slide, what we have understood is what is meant by compaction. It is nothing but mechanical process through which we are decreasing the volume, and because of that the weight is weight divided by volume, this ratio, that is dry density ratio, increases. Okay. Now, some more points here. For any soil at a given compactive effort, the density obtained depends upon the moisture content. Means, when densification is done, obviously we are putting some ramming, or it will be rolled with some rollers, right? How many times the rolling is done, how many times the ramming is done, that will be adding to amount of the energy that will be given to the soil. So now the density achieved depends upon the amount of energy given, as well as it depends upon the water content. That is what is being said in this point. At a given compactive effort, the density obtained depends upon moisture content. Okay. Now here there is a picture of some natural soil before compaction. It is now after compacting, what happened is the same soil particles have come together, and then a lot of airspace which was there has gone out, but the amount of water remains the same or increases sometimes. Now, an optimum moisture content, what is meant by optimum, is the water content at which the soil will achieve a maximum density. Now, if you look at this graph, on this is a graph. Okay. Now, on this axis, what is plotted is water content, and on this axis, what is plotted is gamma d, dry density. Okay, dry density. Here it is water content. Now, when you go on conducting the test, you'll be getting some points here and there, right? And then after smoothly joining that, you'll be getting a curve or something like that, wherein what you can observe is as the water content increases, the dry density also increases fine, but this increase will not be continuous. At some particular point the dry density becomes maximum, then afterwards further increase in water content will reduce the dry density. I have told you dry density. What is meant by dry density? Dry density, again I repeat, it is weight of solids only in the numerator, weight of solids only. So how much is the water here, how much is the air here, it is not a matter at all. What is the weight of solids, that will be there in the numerator, divided by volume. Now in the beginning what happens is there will be the same amount of solids, but there is a big volume. Now when you put compactive effort, the same weight of solids, but the volume has decreased. Because of that the gamma d increases. But this story will not continue. It will be reaching a maximum value. Gamma d will be reaching a maximum value at some particular water content, and that water content is known as optimum moisture content. So that is what is said in this statement. An optimum moisture content is the water content at which the soil will achieve a maximum dry density. It is not possible to compact saturated soil because you cannot remove the air voids. So because of that the volume will not decrease in case of saturated soil, a point to be noted. It should be noted that higher the density of soil mass, the soil will be stronger, stiffer, more durable, and more durable will be the soil. So from this statement you can observe that why the compaction is done. The compaction is done so that the soil becomes strong, stiff, and more durable. That is the intention behind compacting the soil. Okay, here in the picture also you can just see here there is a dry soil and lot of volume of air is there. I don't know whether you are able to see that. Here there are soil particles which are kept the same, weight of solids kept the same. Here this white space is air voids, and you add little bit of water and volume decreases. Still more, add the water, volume still decreases, and then afterwards if you increase further water, what happens is the air voids may be remaining the same, but the volume of water will be adding to the overall volume. Because of that, the volume increases. As the volume increases, this ratio Ws by V, as the volume increases, gamma decreases. This is a beautiful diagram. One can understand. In the beginning, as you add the water, volume decreases, but beyond a particular limit, if you go on adding the water, that water itself will be getting added to the volume. Because of that, the dry density decreases. Okay. Here, what is the effect of compaction on soil properties? There are many. One by one we'll see. It increases the density, obvious. It increases the strength characteristics. It increases load bearing capacity, SBC we call. It decreases undesirable settlement. Of course, when you compact it, there is no space left so that it can settle down. Because of that, unexpected settlement is not happening. Increases the stability of the slopes and embankments. Of course, we are going to study in detail about the slopes and embankment in the advanced geotechnical engineering. But what you can understand is, by compacting the soil, the factor of safety of slopes or embankment increases. Decreases permeability. Obvious, the white space is less. Because of that, the permeability will be decreased. Reduces water seepage. The rate at which the water is seeping through the soil will be reduced because the whites are reduced. Reduces swelling and shrinkage. Reduces frost damage. Right. All this is only because there is a lot of decrease in the whites. Because of that, all these things happen. So this is the effect of compaction on soil properties. Okay, what are the applications of compaction of soil? Now, following are the situations in which compaction will improve the existing field condition. Now, what is that? Compaction of the foundation of soil for house construction. Obviously, you have to, if you want to construct a house, you have to compact the soil. You might have seen that people build plinth wall, and then afterwards fill the soil. Plinth filling is done, and that soil is compacted nicely so that you will be able to place other components of house on that surface. So compaction of soil, gravel, crushed rock, asphalt in road and pavement construction. Yeah, when you construct road or pavement, a lot of material is dumped, and then it will be rolled and compacted number of times. There will be sprinkling of water also, you might have observed. So that is done. Compaction of soil in earthen embankments. So when you want to construct earthen embankments, obviously there will be a lot of soil which will be dumped, right, and then it will be compacted, right. The thickness of the layer comes less than half, then some more soil is laid, and then again it is compacted. So like that, you go on adding layer by layer, and then go on compacting, the soil gets added. So ultimately it may become a earthen dam or embankment for road or something like that, right. So what is done is, layer by layer the soil is added, and then compaction is done in case of earthen dam construction or embankment of roads also. Compaction soil backfill in trenches, right. So dam construction is done. Construction of clay liners for waste storage area. So when you want to put some wastage, right, to not to allow the leachate to pass through, so what you do is you put a thin layer of clay and then compact it so that no leachate will be passing to the ground, right. And then for ground improvement, if you have some ground, and then if you go on compacting it, obviously it will be gaining strength. There are a number of ways of ground improvement, right. There is a separate chapter which is having ground improvement technique. There, obviously, most important part is compaction itself. Okay, here there is a comparison between compaction and consolidation. Because we have a separate chapter of consolidation, you may not understand this. So at this stage I have listed it just, and you'll be able to understand it in a proper manner when you study consolidation. Anyway, at the moment what you can know is compaction is done by the people. It is artificial uh, process wherein consolidation happens naturally. Okay, here in compaction we expel the air content or air voids, the water is added, right, in this case, so that more compact volume will be achieved. Here this consolidation is done for uh, saturated soil, so because of that what happens is expulsion of water itself happens. Here also there is a decrease in the volume, here also there is a decrease in the volume. It is a fast process, this takes a very long process in that sense. This may be taking in hours or days, whereas this will be taking in terms of months or years. Now, possible compaction process is possible in dry or partially saturated soil. The consolidation process is possible only in saturated soils. That is to be noted here. So compaction results in increased density, results in dense packing of soil. Okay. Uh, Mechanism of compaction, or it is also called theory of compaction. You can understand here principle of compaction or mechanism of compaction. All mean the same. There are three ways how it is referred to as mechanism of compaction, theory of compaction, or principle of compaction. So here, when a soil is tested in Proctor mold, so here you can understand there is a mold and then we are going to test. Proctor is the person behind this study. That's why it is called Proctor mold. We are going to study in detail about this mold. Right? For various water contents we get dry density versus water content graph as shown in the figure. So here there is a water content, here there is a dry density. We will be getting some points, we go on just joining them. So what is a characteristic feature of this curve is it increases, reaches a maximum, and then again it falls down. This is typical behavior of any soil in compaction test. Now why it happens so, that I'll try to explain here. The water added in the beginning of the test acts as a lubricant on the surface of soil particle. You can just see here there are dry soil particles in the beginning. Now when you add the water, there will be a layer of water which will be surrounding the particles, which helps them to slip one past the other. It helps the soil particles to move one past the other easily and try to get a compact volume. The volume will be decreased. Now this increases the dry density. I repeat the definition of dry density. Gamma D is given by weight of solids on the top. Purposely I am been writing this weight of solids divided by volume. Now you can just observe in this case also weight of solids is remaining the same. In the beginning large volume, because of compaction the volume has decreased, because of that this value increases. Here also you can just see here there is a slight decrease in the volume, because of that Ws by V becomes maximum. When you add the water furthermore, that point is over here, this increases the density. That is, when the soil particles slip and get into a densest state, the particles will be getting compacted in least volume. This increases the density, increases the dry density. Now after some value of water content, that is after this particular peak, I am talking about this peak, after that, after value of water content, if further it is increased, if the further water content is increased, the density reduces. The water film on the surface of the particle will be so thick, water film on the surface is so thick that the film of the water pushes the particles more apart and the volume increases, leading to decrease in the volume. So you can imagine that particles have got bigger volume of water. Now when the water space is increased, then these particles will be pushed apart. That's why in the same volume V, if you calculate what is the weight of solids, it decreases. Because of that, decreased weight of solids to the same volume will be obviously decreasing the density of the soil, because volume is more but weight of solids are remaining the same. That's why there is a decrease in the density. So that is why it is called mechanism of compaction or theory of compaction. So in the beginning it increases and then afterwards it decreases. That is what is the trend. And this particular point where it goes to the maximum is known as optimum moisture content or optimum water content. Okay. The same theoretical points are repeated here, you can read out. Right? The optimum moisture content is the moisture content at which the maximum possible dry density is achieved for a particular compaction energy or compaction method. What actually it means is the same amount of energy we use every time when you compact. Now the corresponding dry density is called maximum dry density or MDD. The corresponding dry density means for optimum moisture content, corresponding maximum dry density will be referred to as MDD. So MDD is at OMC or at OMC is MDD. There is a correspondence. The water added to the soil particles in the beginning lubricates the contact surface and improve the compressibility of the soil matrix. That is in the beginning. It should be noted that increase in water content increases the dry density in most soils up to one stage, that is a dry side. So this side is known as a dry side and this side is known as wet side. So on dry side, when you increase the water content, the density is increasing. So here water acts as a lubricant. Here water acts as a lubricant. Now beyond this level, means beyond this particular vertical side, beyond this level, and once the water content is increased, any further increase in water, wet side, right, will only add more void space. There will be reducing in the, thereby reducing the dry density. Hence OMC indicates the boundary between dry side and wet side. Dry side and wet side, the boundary is nothing but OMC. Hence the compaction curve as shown in figure indicates the initial upward trend up to OMC and downward trend afterwards. Okay, now how it is tested in the laboratory. This is called standard Proctor compaction test, SPT sometimes referred to as standard Proctor test. Reference is IS 2720 part 7 1987. Now what you have here is the first one, cylindrical metal mold with the detachable base plate. That is this, the first one, cylindrical mold. The detachable base is this and then a collar on the top, right? So inside diameter 101.6 mm, internal height 116.8 mm. These are standards, but when you test you have to actually measure your mold, right? So this has given to 945000 mm cube, right, millimeter cube. But if you want to put it in cc, it will be 945 cc, because you have to divide every mm by 10 so that it becomes centimeter. So 945 cc or 945 ml, one and the same. So mold volume will be approximately 950, or to be exact it will be 945 cc, centimeter cube, or ml, milliliter. Okay, then there is a collar 50 mm effective height. So there is a collar, the height of this is around 5 centimeter. The height of the mold is something like 11 centimeter, 11 and a half centimeter. But on top of it, when you put the collar, it will be around 5 centimeter. Assembly is already put here, right? So base plate, on the base plate you can fix this. Above that, collar is placed. So that's how the assembly of the mold. Now rammer of 2.5 kg mass or 2.5 kg force weight or 25 newtons in terms of SI units. It is made to fall with a height of free fall of 304.8, or you can put it as 30.5 centimeters of fall. So you can say that it is made to fall 30.5. Now you can see the mold in rammer. Now what is the same view it is actually. Only thing is this inside rammer is pulled out in this case. It is pushed inside here. So it is nothing but a rod attached to that. So here inside there is a rod here. The same rod I am trying to draw. At the end you have got a big block of iron in cylindrical shape. So when you lift it and then in a vertical fashion, in vertical manner, when you hold it and then pull this up like that, right? So what happens is that block comes somewhere there and the rod is extending out. There is a way to stop this at that level. Now when it is lifted and then dropped, what happens is this falls down because the length of this is slightly more over here, so it rams the soil. Now this free fall from here to the soil, the bottom part of this to the top part of the soil, right, this is 30.5 centimeter. That is 30.5 centimeters. So that's how the compaction is done, or it is rammed. Okay. Now we'll see next the procedure of test. So here we'll read it quickly. About 3 kg of dry soil with all lumps pulverized and passing through 4.75 mm sieve is taken. The quantity of water to be added to coarse grained soil and more for there is a mistake, more for fine grained soil, so less for coarse grained soil in the beginning. Mold without base plate and collar is weighed and it is say W1, right? So that is missing here. I'll write it one. So W1, this is my one, W1. Okay, here this weight of mold only without attaching the plate and then without collar, empty mold is mold without base plate and collar is W1. So that is W1. The inner surface of the mold or base plate and collar are greased. Water and soil are thoroughly mixed. That will be done in separate tray on which the soil is mixed properly with some arbitrary content of water, and this assembly is placed over here inside the tray, right, and the soil is filled. The soil is placed in the mold and compacted in 3 uniform layers with 25 blows in each layer. Means if I try to show the mold in vertical way, so what you do is you approximately fill the soil more than half, and then when you go on compacting, it should so happen that it will be covering 1/3 of the volume. That is what it means, right? Now after each layer, top surface is scratched to maintain integrity between the layers, and then again the soil is added, again the compaction is done. So there will be a second layer, and then here there is a collar. Because of that you can add more soil and then again compact. When you compact the third layer, it is written here, the height of the top layer is so controlled that after compaction soil is slightly protruding or protrudes in collar. So inside this, very little of soil should be there inside the collar. It should not be standing inside the collar to a large extent. Okay, now again disassemble the collar, remove the base plate, scrape off the extra soil, and if you take the weight of mold with soil, this we call it as W2. Now a representative sample of soil is kept for determination of water content. So some sample from this is kept for water content purpose. Okay, the number of trials shall be at least 6. Now what we have done, you have seen. Now next what you do is you remove all this soil back. Now anyway you have added some water content, you add little more of water, mix it thoroughly, repeat the procedure. You have added the water, right? Because of that, it may so happen that the density would increase. Obviously it increases. Okay, again some sample is kept for water content, and then the density is noted down. Now how the noting is done, that is explained in this. Here there is an explanation in pictorial manner. This is the first trial number 1. Because of that the suffix is 1. Trial number 2, suffix is 2, 3, 4, 5. Now here dry density achieved is gamma D1 corresponding to water content of W1. The height of fall is 305 mm. The rammer weight is 2.5 kg, mass is 2.5 kg. It falls through like that, it falls for 25 number of times. For each layer 25 blows per layer, like that 3 layers. So you will be having some gamma D1 for W1. Now remove the soil, mix little more of water, do the experiment. You will be getting for W2 gamma D2 and so on. You will be getting all these points. Now if you plot them, it may so happen that it will be like this. You pass a smooth curve. Then whatever peak is there, that peak is corresponding to OMC, and here it is MDD, right? Now this part, whatever pink is shown, it is dry side of the dry to optimum, and here it is called wet of optimum or wet to optimum. So that curve is called compaction curve. Now here gamma D is equal to gamma B divided by 1 plus W. This equation is used for calculating gamma D, because anyway we need gamma D. Here also we need gamma D. So gamma D is calculated at gamma B divided by 1 plus W, because you know the water content. Now how to find out gamma B? It is simple. Gamma B is nothing but total weight of the soil divided by total volume. Volume, already know that the volume of the mold, and when you do W2 minus W1 every time, so W2 minus W1, you will be getting this weight of soil. Now what is W2, what is W1? You have just seen here earlier. W1 is empty mold, W1, and then after compaction etc., whatever soil is weight is there, weight of mold plus soil is there, that is W2. So now here W2 minus W1 gives you weight of soil divided by volume, gives you gamma B. Now that gamma B divided by corresponding 1 plus W gives you gamma D, right? Okay, now in this particular test, how much is the energy given to the soil? If you want to calculate, you can just see here, number of layers are 3 layers we are compacting. The height of drop is 0.305 meters. Weight of rammer, it rams, not hammer, so 25 newtons. Number of blows are 25 for each layer. So volume of the mold is 945 cc. Now energy, if I want to calculate, it will be 3 times 3 layers multiplied by 0.305 meters multiplied by 25 blows, right? And then it is of 25 Newton. So here the unit becomes Newton meter, because 25 Newton falls through a height of 0.305, but only thing is number of times it is. So units is Newton meter, or this itself can be told as, you know, that it is joules also, right? So work done is nothing but energy given to the soil. So how much is the soil? 945 ml is the soil. So if you calculate for 1000 ml, means for 945 whatever value is there, that will be there. But for 1000 ml if you calculate, it comes out to be 605.16 Newton meter or joules per 1000 ml. So this is the kind of energy that is given in standard Proctor test for the soil. Okay, to complete it, we'll have one example. What is given in this problem you can read easily. The following are the results of compaction test. Weight of the mold plus wet soil is 29.25. Water content is given. The volume of the mold is given 1 into 10 raised to 6 millimeter cube, or if you want in cc, it is 1000 cc, because millimeter divided by 10 divided by 10 divided by 10. So this becomes 1000 cc. Weight of the mold is 10 newtons. Weight of the mold is given to be 10 newtons. Because of that, this is W. Weight of the mold is nothing but W1. Now what is given over here is W2. So W2 minus W1 gives you 19.25 newtons as the weight of soil, divided by 1000 cc gives you the unit weight of the soil. Anyway, specific gravity of the soil solids is 2.7. Find OMC and MDD. Plot zero air void line. Find the degree of saturation at MDD. Now in this discussion we'll just find out OMC, MDD, and further we'll see the other things. Okay. Now this is how one can calculate. So this is W2 already given. Weight of wet soil will be W2 minus W1, that is it is given to be 10 here. So I'll subtract this 10, it becomes 19.25 newtons, and then bulk unit weight will be that 19.25 newtons divided by 1000 cc. Now if you want kilonewton per meter cube, it will be converted to 19.25 kilonewton per meter cube, right? So if you directly do it, it will be Newton per ml. Sorry, Newton per ml or Newton per cc it will become. But if you want to convert ml into meter cube, you have to divide by 10 raised to 6. And then if you want to convert Newton into kilonewton, you have to divide by 10 raised to 3. So it becomes 19.25 kilonewton per meter cube. Likewise, all the values are calculated. Water contents are already given as it is. Now dry unit weight. For dry unit weight, I have told you gamma D will be equal to this gamma B, because this is gamma B. So that gamma B divided by 1 plus W you have to do, 1 plus W. But water content is taken as a fraction, not as 10. You have to take it as 0.1. So your calculation for the first value, I'll show you. It is 19.25 on the top, fine. 19.25 on the top. Divided by 1 plus W is not 1 plus 10, no, it is 1 plus 10%. 10% is 0.1, so 1 plus 0.1, 1 plus it will be 0.1. Now if you simplify, this will be 17.5 kilonewton per meter cube. This will be gamma D. ZAV line we'll see in the later stage. We'll plot the curve. So if you plot the curve, it will be something like this. Now water content, you have seen it is 10, 12, 14, 16, 18.2. Now corresponding values of gamma D, it has increased and then dropped down. Smooth curve is drawn, and then search for this peak. Corresponding water content, if you try to search here, that will be OMC. So here it will be something like 13 point, yeah, it is written. So OMC is 13.5, whereas corresponding maximum dry density will be 18.85. So this is the most important expected results as far as compaction is concerned. Okay, the other part we'll discuss in the later stage. Hope with this we'll stop. Thank you.